Hello, this video is all about the OCR A-Level Computer Science NEA, which is a behemoth. Every student studying OCR A-Level Computer Science has to do this NEA, and it's a lot of work done mostly on your own, and it's a big deal, right? It takes a lot of effort, like I say. Now, this video is going to go through each stage of the NEA, what I think you should be including, what you should be doing, what things you should be thinking about, how it's marked, all that sort of stuff. So hopefully useful no matter where you are in the NEA process. So it is a big project, but ultimately it's a really, really exciting one. Okay, I don't want to get too negative early on. It's a huge chance to do something really detailed and something which interests you. What you make, you may well, take with you in the future and develop and make even better, and you'll learn lots from doing this process. It is massively exciting, and you can correct me if I'm wrong, but I'm not really aware of any other A-level which has such free reign as part of their course. And I think another key benefit is actually, despite it being a big deal in terms of the time taken, it's actually only worth 20% of the overall qualification. And again, I can't think of another subject which has what is quite a big deal as an NEA, which is only worth 20%. That might seem like a bad thing, but actually I think that's great because it takes away some pressure. If it was worth 60%, that is a lot of pressure, but it's not. The exams are still the more important, but at least you have got that full control over this NEA project. Now, before I move on, I should be really clear this video is aimed at the current OCR specification as I record it, which is H446. Future versions may well be different, and other exam boards will have a lot of overlap, but again will be a little bit different. This project then is marked out of 70. And the exact grade boundaries do vary, and so if you want to get a sense of what mark leads to what grade, Google last year's grade boundaries, just search OCR A-Level grade boundaries June, whatever year it was, and you'll see at some point in that document how many marks were needed for a particular grade. Now usually it's fairly high, and the last one I saw, 63 out of 70, was for an A-star, which is fairly high. And so you can't afford to drop too many marks if you're aiming very high for this. But grade boundaries do change a little bit every year. They generally creep upwards as the course gets older and older. Now, the way this is structured is there are 4 main sections: analysis, design, then the actual solution and your write-up, and then finally evaluation. All of those are in a report. And so you are submitting either on paper, printed, or digitally, this long PDF. And it has these 4 sections. The person marking it will go and read through this. They won't actually be running your code. And so what you put in that report is what's going to get you the marks, not the actual source code in full itself. So much of this NEA is your write-up, is what you are writing about it in your report. The code is really important and gets you marks along the way, but the write-up is key for this particular NEA. Now, the way it works, as you may or may not know, your teacher is going to mark it, and then a moderator from OCR may check it. I've said may because you can't guarantee you will or won't be checked. It's done as a sample. They look at a sample of the work and see if they like the marking or not like the marking. And so it means marks are never final until the moderator has signed it off, until you see it. On results day, the moderator can raise or lower the marks depending on what they think. They're trying to make things consistent across every school. So this project itself, and by the way, I'm using project and NEA interchangeably here. The project is due officially in May of year 13, or at least it has been up until this point. But your teacher may well need it done earlier. If your teacher says it's due in February, or due in December, or whenever, that's your deadline, that is your deadline. Because the teacher's got to mark it, that takes a lot of time. It takes a few hours at least to mark each individual person's NEA. It's very time consuming. And so you can't just rock up a few days before the official deadline and give it to your teacher. Also, teachers get you to do it early because they want you to focus on the exams, which are worth more. Look, if you're doing it late in year 13, it is what it is. But if you can get it done early and you're watching this in a position to get it done early, amazing, because you can really focus on those 2 exams, which are really going to make or break your final grade. Okay, let's go through this project, this report, section by section, and hopefully going through all the things you need to include as you are doing it. Now, the first key hurdle, which some of you might be considering right now, is what exactly to pick as your project. So I said that you've got almost free reign, which you really do. You are making software because we're doing computer science, but ultimately there's not a set scenario you've got to follow or a set of requirements you've got to meet exactly. It is really your choice. Now, the things you have got to do, you do have to have a well-defined user-driven problem. So there's got to be a problem which is clear and will allow you to make some software which has a substantial coded element. So it's not just making anything, it's got to be code, and it's got to be a real-ish problem where you've got users who are going to actually want this software. Now, this word substantial can be a little bit of a red herring, but also it can get glossed over sometimes, I would say, because it's very easy to pick ideas which actually are not really enough for an A-level computer science project. So it might be a brilliant idea, but actually there's not enough actual code to make it an A-level project. So to give you a bit of guidance, if I can give you a few ideas which I would say are probably more than enough, they're good ideas which would allow you to do enough coding, and if I also give you some kind of weaker versions of these ideas, hopefully that will give you a bit of an idea of what is required. So first idea, which I think probably would be absolutely fine, would be if you were deciding to focus on schools. So you think the kind of problem in schools is maybe allocating a timetable to the teachers. This is very, very difficult. I've just gone through it myself in my own school. I went to give different classes, there are lots of clashes, people get unhappy if their day is really busy. It is quite a big problem. And so if you can write a program which actually allocates a timetable to staff, that would be great. Because of that underlined bit would need a fairly complicated algorithm to actually do this. It's not just a trivial problem, that takes a fair bit of processing and actually is one of the more complicated areas of computer science, this sort of timetabling aspect. Another completely different idea might be about gaming. Now, gaming is not an obvious problem, but is perfectly fine as a project if you've got enough coding and enough computational stuff going on. So if it was a video game which has a map which is generated dynamically, as in on the fly, to get progressively harder, again, that provides enough algorithmically to be good enough for an A-level project. And the third idea, which is maybe based on a business, these are also quite popular, might be a just-in-time stock system, which reorders new products just in time based on a big data set, based on previous trends, and maybe some prediction engine, again, would have potentially quite a lot computationally you could write a nice set of algorithms for. So the flip side is where you haven't really got much going on which requires a programming language. Okay, so if you were focused on a school, if you just had a program which was just a database and just stored details of teachers and classes, not really enough on its own. If you stuck an algorithm on top to allocate the timetable, great, but just a database is much more IT. Likewise, a video game, it could be a really nice looking video game, really nice graphics, but if the movement is just simple left-right movement on a 2D screen and the NPCs are randomized, not much processing going on, it's not a test of how good you are at graphical art, it's about what coding can you do. And the flip side of this maybe business system might be, again, just a database. If you just have a stock management system with just all the data, it might show sales and generate reports. Unless they are doing lots of processing, unlikely to get you many marks or be enough for an A-level project. So I think early on, you've got to pick a project. It's got to be one which has enough processing to allow you to produce enough code, which will get you enough marks. Okay, if it's just a simple database or a simple static web page, not really enough for an A-level NEA. Now, your teacher is allowed to give quite a lot of help at this stage, so please do speak to them. They can give you rough ideas, or the more likely help would be them telling you whether your idea is enough to be this substantial or to have this substantial coded element. Now, if I can point out a few areas which in my experience are dodgy and you've got to be careful with, related to the ones I've just shown actually, Database systems. A lot of projects have a database, and that's great. It is a computer science topic, but just a few tables, maybe a bit of SQL, maybe a GUI forced onto it is not really that computer science like. It's much more IT. There's not really much processing going on. If you are doing this allocation and there's some algorithm running, perfect. But a database on its own, not usually enough. Games are, of course, massively popular, but tricky at times, especially if you're trying to recreate a game. It's very easy to either procrastinate or just spend time because you enjoy it, doing things like making nice graphics, making the sounds, etc., which are not going to get you any marks. They're fine if you want to do it and you're still doing this programming, but how it looks and feels is secondary to what processing is needed to make it work. Quizzes are again popular, but I would really avoid unless you've got a very complicated algorithm to mark it if it's not multiple choice, or you've got a complicated retrieval algorithm. Just multiple choice quizzes, even with a GUI, are not usually very high marking. Also, just AI. People mention AI all the time, again, understandably, but there's very little understanding of what they mean. It can be very vague. It can be just like, oh, my game's going to have an AI. And there's never really a description of what exactly that is. So before you start, get clarity, do some research into what AI is, because there are projects which you could do machine learning very feasibly on, but there are other projects which I personally could not even start doing AI with because it's so loosely defined and so complicated. So there are certain projects which lend really well to artificial intelligence and machine learning, but certain projects just wouldn't really work unless you've got incredible skill. Now, the next decision, which will definitely be tied in, is what programming language to use. Now, on the screen are the ones OCR have published and say they are expecting. So the ones on the left are from a specification, so you'll be learning one of these. And ones on the right are things which have cropped up in recent years and they've said are fine. So I think you'll be learning at least one of these in class. You can stick with what you've learned for sure. I do think it's a nice chance to learn a new language. And certain projects lend themselves to certain languages. So for example, Python, you would not use to do an app on a phone. You would use something like Java for Android, or you might use something like, you might not be learning C++, not C+, as it says here, but C++ is good for gaming. And so you might want to use that. So I think don't just stick with what you know. If you feel brave and have got a great idea, go beyond what you've learned, because really that's the point of this project, is to extend your learning and to become an expert in this one area. Just a note on web development. Now, HTML, CSS are of course on the course on their own, and that's including SQL as well. They're not going to get you many marks. It's got to be used with a programming language, which they are not. So if it's web development, JavaScript as front end, PHP back end, or similar languages would be great for getting you marks. Just how it looks and how it interacts with the database is not really the focus of this project. Now, if you're going for a language not on this screen, make sure you get approval through your teacher. Your teacher is able to help, like I said, at this stage, and contact OCR if they're not sure and get approval just to be on the safe side. Obviously, a big fear would be if you rocked up, submitted a project in a random language and it got rejected at the final stage. It's worth getting this sorted early on. Now, one thing I really want to emphasize, which is massively important, now you need to have a GUI. That's something OCR have been very clear about. I think mainly to distinguish between GCSE and A-level projects. GCSE, you might just have command line programs, but a GUI is a graphical user interface. It's where you've got nice windows, you've got a front end which actually resembles a real program. And that's really important. Now, I've put an asterisk there because there are a few ideas which may not need one. So the main one I can think of is if you've got, say, a robot, you might just have a yes or no to launch this program, and it might just run on the robot and there's no actual interface apart from that. But if you have got an idea which you think you're going to skip the GUI, again, get that approved. But you need to make sure when you're learning these languages or you're thinking of requirements, you're aiming to make a GUI with at least one window which has got buttons and so on. Right, before we move on to analysis, all I'd say is picking a project is definitely tough for some people. Some people within seconds have got an idea and are happy. Other people really deliberate over it. Certainly if I was in your position, I would spend weeks being indecisive because that's my personality. I think ultimately you're doing this to get an A-level grade. This is not necessarily your great idea that's going to make you loads of money. It just has to be a project which is feasible and in your scope, within your skill set. It doesn't need to be a huge, fantastic idea. Keep it fairly small, which you can add features to as you go. And please do make use of your teacher to keep you on track and to keep you grounded and to make sure that it is good enough for an A-level project. Now, I'll talk more right at the end on some more tips about this, but for now, let's start with going through how analysis works, which is our first stage in your report. So we're looking for big subheading, analysis, and this is worth 10 marks. So 10 marks out of the 70 is this first stage. Now what this is you setting out what your project is and why. Once you've picked your idea, you're now telling the person reading what the idea is and why you are doing it. Now, when I'm marking analysis, my test for whether it's good or not is this. Could anyone reading this analysis understand what this person is doing and why? So it's not just a computer scientist, it's anyone. Are you being really clear? Have you gone through what all the jargon means? Have you given a really nice background? Anyone reading it with a brain should be able to understand what is going on. Now, let me show you the mark scheme in just a few seconds, but I just want to start with how I would personally structure this first section. So what I would do if I was tomorrow sitting down and writing analysis. So first stage, I think, is really clearly identifying what exactly the problem is. Don't get too hung up on the word problem. Doesn't need to be a life or death problem. You're not solving climate change or racism or inequality. It's not necessarily that kind of problem. It could just be, oh, I like video games. There's not a good video game on this topic. It can be a fairly minor problem, we could say that. But be really clear what it is and why you're doing this project. Then you should be researching this problem, which will include finding out what other solutions are out there. Maybe there is a system currently being sold, but you think actually it has some limitations, and so you go through these limitations and say why your solution would be better. But we're looking for a few pages at least, going through what else is out there, but also what exactly is this problem. So the example I always give is chess. I've seen quite a few chess projects in my time, and the good ones explain what chess is. They go through the rules, not in pages and pages and pages of detail, but they go through how chess works, what are the main rules, how is it shown, what's the notation, what rules are they going to leave out because they're too complicated. That's the sort of thing you need, because you've got to assume this is some random person reading it. They might not understand the very niche video game you're referring to, or they might not know this obscure board game you're basing your problem off. Make sure you are at this stage explaining how things work, introducing keywords, so the rest of the report is easy because the person reading knows what's going on. Then, at this stage, I would move away from what the problem is and move more towards about what you're going to do about it. So what exactly are you proposing that you are going to do? What is your software going to do that hopefully addresses at least partly this problem? And at this point, we should be taking in stakeholders. You could mention stakeholders in the very first few paragraphs, but if not, start mentioning it here. So a stakeholder is anyone interested in your solution. So most often this will be end users. Who are the end users likely to be using your program? Sometimes it's ultra specific and it is one person or one business or one very narrow demographic. Other times it can be more broad. So for example, if it is a program on education, your stakeholders might be any teacher. And so it's quite a broad group of people. But at this stage, in an ideal world, you'd be actually having some dialogue with these potential end users to try and figure out what their needs are. Now that's not necessary. You don't have to drag in some poor person you've found to have a nice chat with you. You are able just to do this based on your knowledge and based on your research. What do you think they're going to need, what requirements will they have. But the strongest NEAs actually will do maybe an interview, maybe a survey with one or more people. And that is good because it can produce quite useful data. You can show us a few graphs, a few charts, and that will definitely help you when you move on to justify why you've chosen what you've chosen. Because you can say, oh, I've chosen requirement 4 because so-and-so said that would be a really useful feature. It helps you back up the points you're making. Now at this point, people can start to make up things. They can make up this stakeholder, they can make up this end user. It's best to make it as realistic as you can because it can often be quite fake this stage. The dream would be if you've got a local business, you know people working there and you can interview them. You've got contacts you can use. That'd be the dream, but I realise that's not always possible for every person. So once you've gone through what end users will likely need, you should now do some more research, this time much more on your solution. So in my view, I would separate research with a problem and research with a solution. Now you might not do that, you might combine it, you might merge them, fine. Personally, I would do this afterwards and focus much more now on what technologies could be used. So what languages could you use? What frameworks are there? What libraries are going to help you? Are there bits of code you could borrow and obviously reference? At this stage, that's a research I would do and put this in my analysis. Then we're getting really specific and starting to go through what actual things are we going to put in our program. You might have been fairly general up until this point, but now we're getting into the nitty-gritty of what specifically is going to be there. So you need to both identify and justify this for top marks. Identify might just be a bullet pointed list or a table with these features in, but justification is where you're saying why you're doing what you're doing. And that's where having data to back this up would be really useful. Now, this should be in the form of success criteria, which we'll come back to in a few minutes' time. And finally, the last thing, it's a bit of an oddity actually, I think, but you need to get high marks, justify the hardware and software requirements of the solution. So what hardware is needed, what software is needed, but we'll come back to that in a couple of minutes. Now, let's now look at the actual mark scheme, because what I just went through is how I would personally do it. But here is the mark scheme, and you could tweak the ordering or make it a little bit different. As long as it matches the mark scheme, the ordering and so on is not very important. So what's on the screen here is what I've described as the highest level analysis. Well, what does this mean? Right, let's have a look at the OCR website then. This should be very familiar to you, especially as you go towards year 13, especially the specification, which contains all of the details of what you've got to know. And in here, not everyone will know this, but I need you to. There are details on the NEA which are going to be really useful to you as a student, not just as a teacher. So we can skip the exam content, but we've got content for the NEA a few pages down. Now, this first part is really the specification for the NEA. So it's going through all of the content you should be including, all of the content you should be taught, ideally, in order to be able to do the report. And so this is useful, worth printing and having a look at it. But I would say the more useful bit is the actual marking criteria for the NEA. So because it's a general project, there isn't a specific mark scheme for that particular project. It's a general one which your teacher will use to justify to the moderator the mark they have given you. So there is criteria for each part of the report, and for each there are 4 levels, starting low, ending high. And of course you're looking at the last column, the high column, to try and maximize the marks you can get. But it's interesting seeing how they kind of progress from low to high. So for example, analysis, we've got a lot of identified, where you're just stating stuff without much detail, maybe quite vague, maybe quite loose. Whereas as you go towards higher marks, you're now describing, you're doing actual research, and in particular, in the top mark band, you are doing justifications, so saying why you're doing what you are doing. Now this part of the spec should become your main friend when you're doing the NEA, especially your write-up, because just make sure your write-up matches the mark scheme. It's infuriating if you have got a great write-up but you've missed one of these points, because it can really bring you down a little bit. The way it's marked is the teacher and then the moderator will have a look and try and place you within one of these levels. Where are you roughly placed? Maybe not always every single thing or every single thing done perfectly, but roughly where are you placed? And then within the mark band, they'll put you at a particular mark depending on how well you've applied these criteria. Okay, let's start then with the very top. So the first point the market is looking for is, have you described and justified the features that make the problem solvable by computational methods, explaining why it is amenable to a computational approach. Now, a fairly wordy start to the mark scheme. Not every bullet point is like that. I'm not convinced amenable is quite used in the right context there, but never mind. Really, this is saying, why is a program suitable for this problem? Why should you be doing a program? Why not be doing, volunteer work in real life? Why not be doing a book? Or why are we doing it? Why are we doing computing? Why are we making a program for this? Now, that's how I'd sort of introduce this paragraph, which could be early on, it could be a bit later in analysis. But the meaty stuff here is specifically what parts of this problem lend themselves to something computational. It's going back to my first couple of slides where I was showing those good projects and bad projects. The good projects has something computational which could be programmed. The timetable is an optimization problem, that's computational. The video game with a map generating has got some algorithm, maybe even AI. That's computational. And actually, for this part, I would essentially pick out words from the specification. Now, this picture is way back in the paper 2 specification, and it's the computational methods subtopic. Now, here is what the person writing the spec listed as computational methods. And so if you can name drop some of these into analysis, that's perfect. So the kind of key computational methods are things like decomposition, abstraction, then you've got kind of more applied areas like backtracking, heuristics, and so on. So you're looking to think, what exactly fits with these, right? Where have we got decomposition? Where have we got abstraction? Where could we do some data mining? For example, my just-in-time stock system might well need some data mining to be able to order stuff when they're needed, etc. You're looking to bring in these theoretical terms into your analysis so that you're being clear that you're not just doing something really unambitious, you're doing something really computer science-y, and it is computational and not just really simple. The next spec point I won't dwell on as much because we've covered it a little bit already about stakeholders. So you've identified the stakeholders and describe them, who they are, what features make them your stakeholders, and explaining how they will make use of your solution and why it fits with their needs. So it's who might use it, what features will they want, and why, crucial. And if you can get some data to back it up, perfect. The next point, again, we've discussed a little bit about research. So you're looking at existing solutions to similar problems. It might not be a direct competitor, but you're looking to pick out what similar problems are there. So for example, if you've said, I'm going to make use of a backtracking algorithm, maybe for something like Sudoku, you might find some other Sudoku apps, but find other games which make use of backtracking as well. So you can include those and pick out some useful approaches. So again, we're looking to justify here, not just state what you found. Now, this section I think is really good for both the reader. You can really set the scene for the person reading. Like I say, if you are doing something quite obscure, it's especially important you start to explain how it works and the key aspects of it. So it's for the reader, but also for you, because hopefully your research won't just be an exercise in ticking this marking point. Hopefully you'll find something useful, you'll find a nice idea, you'll refine your approach based on what you have researched. I would caution here about making this too textbook-like. You're not writing a textbook, despite the temptation of some people. You're not looking to, write a Wikipedia page on Dijkstra's or, go into loads of detail about what you're doing. You should introduce key terms and discuss the algorithms you're thinking of, but don't get too heavy too early on, although do explain stuff. And speaking of Wikipedia, make sure you do cite stuff. I won't go through how to reference in this video, but if you don't know how to reference, find another video on it. You should be really careful about plagiarism. You should always put down a link or put down credit when you've used a quote or used a definition or used some code from somebody else, and start this early in analysis so you're showing the person marking it that you are taking this seriously. But as I've kind of said before, do explain everything, don't go into loads of detail, but please don't assume the reader knows this project already. They might do, but still keep it very well explained. The next step, as I introduced a few minutes ago, is actually starting to get more specific and identify what essential features are there going to be and why. So the whole point of the previous sections, both from the stakeholders and the research, is that it should feed into what you're doing. If your key features are completely different to what the stakeholder wants and what you've researched, that looks very weird. It's meant to be feeding together. Quite possibly you'll have some brand new ideas, which is perfect, but we're looking for stuff which the stakeholder wants and stuff which you've found through your research, so that it flows together and isn't disjointed. Let's spend a few more minutes on this though, because it is absolutely key to clearly set out what exactly you're going to do, because it's going to really affect your testing later on, and you need to know what you're aiming to do. Having an aimless project is a bit of a nightmare. So let's focus on these two marking bullet points and going through what I would personally be doing if I was doing this myself. Okay, so I would personally start by setting out what exactly are the high level objectives. So high level, I mean fairly abstract, fairly general, fairly vague actually. What are the main things you're looking to achieve? Again, hopefully fed in from the research and the stakeholder. So you might have, say, 8, 10, 12, etc. objectives, not tons, not 4, which roughly set out the main features of your project. I would personally almost bullet point this with maybe a paragraph explaining each one, explaining why it's important. So for example, one might be your GUI, which I've said you pretty much need to have. So you might be, I'm going to make a GUI to navigate the different pages. Great, bit vague, but fine for a general objective. Another one might be making a login system so you can gain access to secure areas, etc., etc. That's a fairly broad objective, but we've got to get more detailed. Then you might start to get moving towards more specific requirements. So what actual features are needed to meet these objectives? If they're quite vague, break it down into specific things which are needed. So you may disagree with some of these ideas, but let's say we're doing an app for a tablet, for a business, say. This GUI might be labeled 1. Then you might have, say, a requirement 1.1, which is having a main menu window. Then you might break it down even further, because that's still quite vague, and have sub requirements 1.1.1, 0.2, 0.3, and so on, which are going to the more as much detail as you can. So one might be just having the logo and number, very simple. Another one could be you can resize it and it will adapt if you rotate the screen, etc., etc. Now you might have, say, 8 objectives potentially. You might have, say, 30 requirements. That's just a ballpark figure, which are very tightly defined. But you'll notice that actually objectives and requirements are not used here in this context. Requirements are used for hardware and software, which is not really what I mean right now. But what is mentioned are success criteria. And so we must have those. These first two are what I would do to help me move towards success criteria. But ultimately, you've got to have something labeled as success criteria. Now, these are a pain to try and explain, I've got to be honest. Success criteria are statements you're going to use later on to figure out if you have been successful or not. So they're very, very similar to requirements on the surface, but they tend to be phrased, they're more like, how will you know what you've done is good? So for example, you might have another table which ties directly to your requirements, and you're just slightly rephrasing what you've written to be more about how you'll know you've been successful. So having the logo and number could be reframed as being, well, I've got the company information present. Then you should really be saying, how are we going to test this? How are we going to know it's been successful, well, I'm going to show a screenshot. This column is not necessary. You could do this as a few paragraphs. The way you do it doesn't matter. I just think be really clear about what exactly are you going to be looking for when you are testing. Because ideally, the success criteria, again, you might have, say, 15 good ones. You might have, say, 30 slightly more broken down ones or more. Ideally, you're going to be able to take these and paste them later on in your report and do some testing. Maybe stick a few more columns on where you're actually showing evidence that these have been met or not met. Which is why this is important, because it's going to be used again and again later on when you are doing the many tests required for this project. Now, as I've said a couple of times, these should be as specific as you can be. It does say measurable on the spec, which is linked to this, right? To be measurable, you've got to be able to actually tell if it has been met or not. If it's incredibly vague, you can't measure easily whether it has been met or not. Ideally, somebody else could test your program for you because your table is so tightly defined. If you're vague and what you've written is subjective, it could be interpreted differently. Very hard for somebody else to test this with any confidence. So in my example, I've tried to be fairly measurable here. So for example, this resizing requirement, I've said the user can drag the window and rotate their tablet without the GUI crashing, etc. I think that's fairly measurable. You could argue that it could be more specific, but it's better than just window can move, or it won't be buggy, or it will load fast, or it will look nice. Those are the sort of things we're looking to desperately avoid because they're subjective. What you think's nice might not be nice for somebody else, and so the more specific and assertive these are, the better. And I haven't put it in my example here, but you must justify these for top marks. Maybe in the table, maybe below the table. Why are these important? And again, we're looking to feed back into the stakeholders, feed back into the research. And also for success criteria, why are they relevant tests to do later on? Why is it important to test this to tell if it's working or not? Okay, moving on, because we're not even done with analysis yet. It is really important for only 10 marks. So the last parts are not actually particularly tricky once you've got the success criteria out of the way. The next thing to do, which I would personally do after the success criteria, but it doesn't matter, are the limitations of your solution. So what areas are you thinking that actually they're not going to be fully complete? What things have you decided not to do that somebody else might have done, and why? So why have you chosen not to do that thing? Why was it not as important in your mind? Now, one thing I would try and avoid at this point is blaming time. So of course time is a factor in many areas, but don't use that as your stock answer for why you didn't do something. So I've had my own students in the past have lots of optional requirements, which are optional because they're saying, oh, I've got such a tight schedule, I've got a deadline coming up soon. And I'm reading it thinking, you have had a year to do this. It's not really a tight schedule. So time is a factor, but try and think of, why for a stakeholder is this advanced feature actually maybe not as useful as this other feature. Try and limit your scope, but justify why it should be how it is. Ultimately, you're one person doing this project. There are, I'm sure, many more features you could do, but you've got to pick a core set for have processing and have something computational. The rest of the kind of nice, flowery features could get left for another project. Now, the last thing is related to requirements, but kind of a different kind. These are software and hardware requirements. So essentially, this is referring to get the solution working, what is going to be needed by the end users. If they were to take your code and put it on their own computer, what would be required? And based on this, justifying why this is acceptable. So for example, if your program is so power hungry that it needs a top of a range gaming computer, probably not useful if it's aimed at primary schools, right? You've got to try and justify exactly how you're doing things. Again, for example, if you're doing, say, a GPS related project, well, surely you need to have a phone to to be able to do this. It's not really good enough doing it on a desktop computer. So that is where you can start to bring in these justifications, ideally quite specific. So what particular unique things are needed for this project? It might be you're working on a particular OS, you've only written it for Windows or Linux or Mac, or there's a particular framework you've got to have installed, or a library or a device. You know, for example, Python, if you're doing machine learning, you've got to install lots of different libraries, different modules. If you took that code and ran it on a school computer, probably wouldn't work because the libraries are not installed and so it couldn't be ran. This is where you start to go into detail. Don't bother listing loads of stats which you've made up. You know, it's got to have X amount of RAM, a hard drive of X gigabytes. Unless there's a good reason, specific details like that are not as important as for kind of installation requirements you might need. Oh, okay, analysis is done. Phew. A lot of I went through. I went into quite a lot of detail, partly because it is what I would call low-hanging fruit. It's only 10 marks, but it should be a relatively easy 10 marks in the general scheme of things. It is crucial for setting up the rest of the project, but ultimately, what you need to include is fairly set. And every project might have a different order, and of course the content will be different, but what is there as subsections are all the same across every single analysis. Okay, so it's fairly straightforward to do analysis if you just follow the steps I've gone through. Design is worth some more marks, it's worth 15, and so should be probably a little bit longer than analysis. Now, just to give you a guide, if your analysis is 4 pages, that is, I would say, almost certainly too short, unless you're aiming for a fairly low grade. If your analysis is 40 pages, I would say that's almost certainly too long. You know, I don't want to give an exact range, but when I think back to what my own students have done, probably between 8 and 15 pages is fairly typical for analysis. If we're just below or just above, that may well be fine. Of course, it's quality, not quantity. Now, design could be a little bit longer, could be, say, between 15 and 20, 25 maybe, partly because a lot of this is diagrams which take up space, okay, but don't obsess over how long your report is. Now, I said for analysis, it's about whether anyone could understand it. As we're getting more technical now, a test for a good design section is whether another programmer could understand it. So not just anybody, but we're looking at programmers now. So essentially, the point of design is you are deciding how the program is going to be made and why before you start it. As you'll know from experience, I'm sure, if you jump into coding straight away, you often get stuck because you haven't really planned it out properly. And so design is trying to do this planning before you begin. And we're looking to make it really clear so that in an ideal world, some other competent programmer could take all of your designs and make the solution themselves. So if only you can follow it, that's not a great design section. Which is why we want to try and make it not too language specific. I wouldn't worry too much about this, but if every single thing you're writing is unique to C++ or to Python or to JavaScript, that's maybe a sign you're getting too detailed too early, because let's say you're doing an app. Well, what you're containing here should really apply to any language, any operating system. It should be fairly generic. The actual implementation is not as important right now, but like I say, I wouldn't get too hung up on this because this is not a professional product you're designing yet. So again, if I can start with giving a kind of suggested order for this, which you can change, you can tweak, you can reorder, it's absolutely fine. This is again just what I would personally look to do. I would look to start with a nice overview of my system. So what are the key components of it? This will link to your success criteria, of course, but really this is you doing decomposition. You're decomposing it into modules, into subroutines. Maybe it's an object-oriented solution, and so on. So you're really showing the user roughly how, showing the reader roughly how this will be structured. Then I'd get a little bit more detailed, maybe look at each individual part. I would personally start with going through the key data structures. So how are the data being arranged in your system? Ideally with some examples. So if you're saying, oh, I'm going to use a dictionary to store, I don't know, user information, great, show an example of this dictionary with user information. And that might be fairly language specific, but that's probably okay. Examples are always good in this case. Then I would, after you've gone through all your data structures, that might include your database actually, you would ideally then go through your key algorithms needed. Now, if you've picked a bad project, you might not really have any algorithms at this point, and so it's going to cost you marks. It's why I spent all that time talking about what is substantial and not. If it's substantial, you've got hopefully a few different algorithms you can go through. So for example, if you are doing a GPS system with a shortest path program, like a sat nav almost, you're going to have a algorithm, something like Dijkstra's or A star, and you go through it, give some pseudocode for it, go maybe hand trace it, give an example of you going through Dijkstra's on an example graph. That would be amazing for design. Then, quite an important aspect of later sections as well is usability. I would at this point introduce what are the usability features and start designing these. So usability is all about when the user is sat in front of it, how are they going to use it, how do they interact with your system, what's going to help them understand what to do, what are you expecting them to be doing at various points. This will be designed here. So it's a good place to put your GUI designs. This could be just a sketch on paper, it could be mocked up in PowerPoint, for example, and justified saying why you've picked this color scheme, why there are buttons here. Ideally, there'll be some accessibility features. You know, if someone's colorblind, is there a way to tweak the colors? Is there a way to increase the font size, etc.? That may be ambitious and unnecessary in certain projects, but it's a nice place to put it. Now, expected use cases are really what are you expecting the user to be doing. There are a few nice diagrams you can use for that, which I'll mention in a second. Then maybe, to slightly undermine my big red point at the top, you might want to get a bit more specific. So what specifically are you expecting the code to have? You know, what subroutines are needed? What functions and procedures are you going to have? What classes are you going to need? Exactly how will the database be structured? If you have a database, you don't need to have one. You know, what primary keys, foreign keys are, maybe what SQL is going to get used. And also another important aspect is validation. So where are you going to validate? In your GUI, presumably there's going to be some user data entered. That should be validated and checked to make sure it's safe and won't break your program. Then the last point is again important and very, very easy to forget, is about testing. You're in design, before you even start coding, kind of planning out how you're going to test it later on, and focusing in particular on what data you're planning to use and why. I think why is the operative word in this section. To get high marks, you've really got to justify, you know, why you are planning it like you are planning it. This section will definitely be a mix of diagrams and text. A lot of the analysis is just text, maybe some tables, maybe some bullet points, but a lot of just paragraphs. Whereas design will be a mix of diagrams and text. And make sure you use the text to explain the diagrams and, like I say, justify your thinking. Why are you doing what you're doing? It's very common to have flowchart, class diagram, system diagram, data flow diagram without any attempt to explain them. It's not really good enough. If you've done a diagram, please do explain it and say your thinking. Now, the actual diagrams, some of which I just mentioned, will depend very much on your project. The ones I've often seen are things like flowcharts and pseudocode. Really, you should have some pseudocode. Structure diagrams are pretty popular for that first decomposition. Subroutine listings, where you've got a table saying what subroutines you've got and parameters, return values, and so on and so on. Now, a lot of these you might have to Google to understand. Some you might know. And like I say, some are not relevant to your project. If you are not coding in object-oriented style, of course, don't do an object-oriented class diagram. If you are not doing a database, not really much need to show data dictionary is not as important in that case. You know, an MVC diagram are fairly nice for web apps if it's structured like that. It just does depend on what exactly you're doing. And this is not a complete list. You might come up with a nice different diagram. You might spot a nice diagram in an exemplar which you want to use. So I would be a bit like a magpie or a treasure hunter at this point and kind of pick out nice diagrams you've seen and read about, but don't include everything. I've seen projects where somebody's clearly seen a list like this and put all of them in their project, and a lot weren't relevant or needed, and they wasted a lot of time making nice diagrams which weren't even relevant for their project. So It does depend. This will take time for you researching how these look and why they should be used, but it's something needed for this section. And I will say, for your benefit, please do start design before programming. It's very tempting just to dive straight in, and it's tempting to do this section after you've coded. So please do start it. But if we're honest, it's unlikely you're going to write design and make it perfect before programming, because quite honestly, a lot of the time you won't really know what exactly you're doing yet. You might have aimed to do this thing, then you try and do it and can't do it, and so you have to adapt and adjust your plans. And so I would almost do a first draft of these before programming, but then of course before you submit your report, going back in, tweaking it to match what you actually did. So please don't neglect it at the start, but don't be afraid to go back and modify it to match your later code. You'll notice that none of these diagrams are language specific. The whole point of pseudocode is that it can apply to any language almost, which is what I was saying earlier about not making it too specific to one language. Try and keep it quite broad so that these could be applied to any language pretty much. Okay, right, let's have a look at the actual mark scheme for this. I won't pick this one apart as much because a lot of what I've said matches the mark scheme happily. So you can have a read if you want to. I think what is more important to focus on right now are the last two bullet points, which are related to testing. I want to focus on these because actually we've got two kinds of testing in this project, and you getting your head around the two different kinds is essential to get high marks, because I'm sure people complete this NEA without really understanding the difference between the two, and so that inevitably will affect their marks. So we've got two types of testing. We've got iterative, which is this penultimate bullet point, and we've got what they call post-development, also called terminal in certain cases, which is done after you've finished coding. Okay, and you need to, in design, before you've done any coding, in theory, you need to have mapped out both of these kinds of tests. Okay, so iterative testing is where you are writing some code, testing it, and then improving it if you find any issues. So as we'll go into, the actual main programming part of this project is very cyclical. Do some code, test it, fix any bugs, test it again. When it's all fixed, move on to the next thing. You're building up your solution step by step, improving it over time by doing lots of iterative tests. So really, when we think iterative, we're thinking like, what are the tests you're doing when you're actually doing the code? Okay, so generally these tests are what you might call white box tests. White box testing is where you're within the system, you know exactly the code, you can see the code, you're focusing on individual chunks within the code. So for example, you might, in design, have listed 10 big subroutines you're going to need. When you've written one of those subroutines, you might do an iterative test on it to fix any issues before you tweak it. So it's very tied to the code, less so the end result. You're testing it in small chunks as you go. Whereas post-development, as the name would suggest, is done after you've finished developing the program. So once it's all done and all of these iterative tests have passed, you are then testing parts of the solution after development. And the word module I'm going to use quite a lot, and it's quite a general word. There's a distinction between modules of the code and modules of the solution. So for example, you might have an encryption subroutine. During iterative testing, you might test just that single encryption subroutine, whereas in post-development, you might test the whole encryption system. So you're seeing, is it actually encrypting passwords? Is it not? Whereas before, it's just that one subroutine. Whereas later, it might be a few bits working together behind the scenes. The point being, post-development doesn't really care about the underlying code. We are assuming the underlying code is pretty good at this point. You're testing, does it work together? Is it useful to the user? We're not looking at what is under the hood, the actual code running. We're looking at what it's doing. So, two distinctions between the two types of testing. You've got to, in design, plan out these two. Well, how would you do this? For iterative, either in prose or I'd recommend as a test table, I would plan out what important bits of code need to be tested as soon as they're programmed. As we're going to talk about, the danger is you write a line of code, do all this testing, write another line of code, do all this testing, which is nonsense, and it's going to waste many, many hours of both you and the person reading. What is better is if you pick out what are the key bits of code, maybe 5 bits of code, maybe more, what needs to be tested after it has been programmed. Ideally, because it's really important for something later on. Maybe your whole solution relies on your database, or the whole solution relies on the back end of your web app. And so you do that important bit first, test it, move on to the next important thing, test it, move on, and so on. So really mapping out what are the chunks you're going to test and why. For post-development, it's similar, but it's much more tied to your success criteria. So you could, if these are decent, just Control-C, Control-V into design and state how they're going to be tested and include what test data there is going to be. So as you'll know, hopefully from the theory side of this course, it's important to test your programs using a range of test data. The 3 main categories are normal, boundary, and erroneous. Occasionally invalid is dropped in, which I'm going to ignore because I'm not sure that makes sense. So normal test data is where you are expecting this data to be used. So maybe for a sign-up system, you're expecting a Gmail email address to be put in. Boundary data is where it's sort of on the edge of being valid or not. Maybe somebody has got a very, very rare email address or from a strange domain name. That might be boundary data. Boundary data is either valid or invalid depending on the context. And erroneous is completely wrong. You don't want it to be typed in, but you should test it to make sure your program doesn't break. A lot about development is making it robust, ensuring things don't break when the user does something silly or does something deliberate to try and break it. Your code should adapt and not crash. And so we're looking in design to be really clear, what data are you going to use to test it? And try and use these categories and be clear that you're not just testing the normal data, you're testing the slightly riskier data as well. So I think tables are really useful here, but again, it can be a mix of tables and paragraphs or just paragraphs. But spend a page, maybe a few pages, going through how you're going to test, what are you going to test, and how are you going to test it. This is required for top marks in design. Now, moving on to the largest bit of this project, which is still only 25 marks. It's not a ton, but bear in mind this is for your actual coded solution. So the actual code you're writing is only worth 25 marks, although of course it has a knock-on effect on evaluation later on. So when this is marked, there are 2 parts to it, which are not and shouldn't be headings in your report because they're both joined up, they're just marked separately. Okay, so the first part is 15, second part is 10 marks, but like I say, they're really combined from your report's perspective. Like I've mentioned, iteration is very important to OCR in this NEA, which I do understand. Personally, I'll say this quietly, I'm not a huge fan of this being in the NEA, but totally understandable. A lot of real software development is done in an iterative way. It just makes this section at times quite confusing, I would say, but we can try and mitigate against that. So essentially, the point is you are doing some coding, you are testing it, you are fixing it, and doing this a few times to have this iteration, to have this loop. So the point is, several times in this section, you should write some of your code, which I'm loosely going to call a module. This might be a subroutine, it might be several subroutines, it might be just part of a subroutine, depends on what you're doing. You then show the source code, so paste in what you've done and discuss it. Why have you done what you've done? Then you'll test it using your plans and the test data you've set from design. Ideally, some of it won't pass, some of it will fail, and you have to review this, so what worked, what didn't work. And the things which didn't work, you need to iterate and go back to step 1 to fix these issues before repeating this process again, but only for those broken bits. Right, if 9 of your 10 tests passed for this module, those 9 tests get skipped, only the one broken one is discussed again. So we have this kind of iteration even within individual modules. So you might have, it depends on how you approach it, you might have say 5 modules you're doing, you might have say 10, you might have say 30. In an awful case, you might have say 100 if you've really designed it badly. But we have this going back, fixing stuff, documenting it. There's a lot of you showing your process, not just your final answer. You're showing your process throughout, which is why, if you are able to, at this point, start documenting this as you are doing it. Now, analysis and design, it would be a mistake to skip those, but you could hypothetically do those last and just match it to your code. Not a great idea, but you could. It's doing this bit in retrospect is going to be very hard because you've got to, okay, let's say you've got your solution and you haven't bothered doing any of the write-up. You've now got to try and break apart that solution and fake bits not working. Maybe you're going off your memory a little bit. You've got to try and build it up in reverse, whereas you're meant to be documenting it as you're going along. That'll be much, much easier for you. So faking it is going to be hard and also come across, I think, a bit fake, funnily enough. Now, if you're in a position where it's too late and you've already sort of programmed it, you're going to have to fake it essentially, but try and avoid that if you are in that position. What else is worth saying here? I think documenting it as you're doing it is great. I would not make it look nice at that stage. I would be coding and just putting in screenshots, putting in test tables, putting in your code as you go, then tidy it up later, because you might want to, at the end, streamline bits of it and delete bits of it. Don't spend ages building up perfectly as you go. Just put in your evidence and then tidy up and fit to this structure a bit later on. Okay, let's now go through each individual marking section. Like I say, these are not sections in this part. Have the subtitle developing the code solution. Don't have subtitles like iterative development. So this is the top mark scheme for this, and I want to separate it into two parts because some of these bullet points are just about your code and some are much more about the write-up. So the write-up points are highlighted in pink here in my interpretation. So let's go through this bit by bit. The first bullet point says you provided evidence of each stage of the iterative development process, which is what I've just said, doing all of those parts. I'm relating this to the breakdown of a problem from the analysis stage and explaining what they did and justifying why. So you've broken down into hopefully success criteria and objectives, and you've got each clearly in this section of your report. So let's say you've got 8 objectives. I would be really tempted to have 8 parts to my code solution part, and each one you've got this iterative process to build it up. That's what I would personally do to make it really clear and not have a million mini sections you are slowly and tediously building up. I would kind of keep it fairly big and iterate within those fairly big chunks, but always justifying why you've done what you've done. Why have you started with that point? Why have you done that technique? Why have you coded it in that way? What difficulties did you have? Etc. etc. So just to summarize that again, I would effectively describe the key parts of your system, how you developed it and why. Don't spend time explaining how input works or explaining what an if statement is or what a text file is. That's not what this is. It's about what tricky stuff have you done, how did you do it, what stuff did you have to fix and why. Now the next bullet point is related to this bullet point I've written. So throughout this entire section, make sure you've got your source code constantly there and only the source code relevant to each part. Don't dump in your entire program after each module, just the relevant source code at a time. So it will be quite broken up. Either do a screenshot or paste it in. If you can paste it in with the colors would be, I think, even better. Screenshots can obviously be a little bit blurry and low res. So the next bullet point of the mark scheme is providing evidence of prototype versions of your solution for each stage of a process. So prototyping is where you are effectively producing incomplete versions of your code, but over time you're kind of steadily building these up and improving them as you are iterating. So what this means in effect is just show your source code building up over time. So you might write a subroutine and it's a bit buggy, it's not really working. You then test it, you find the bugs, then you build it up and improve it, and you show that improved code. So I'd be tempted here to put side by sides, if you can, at various points, to be really clear that on the left is my initial prototype, on my right is my final version. Look how much better it is. Look at how I've fixed these bugs. I think that's quite a nice way to really signpost that you have got prototypes and you've built up your code as you've gone through. And the last bullet point is about showing review at all key stages in the process. Key stages being a operative term here. We're not looking for you to sign off every single line of code. We're again looking at the key parts. What are the key chunks, the key modules within your solution? So you need to, after you've tested it, be really clear about what remedial action was needed, what action was needed to fix the issues you had. That's what that means, remedial. So what did you do to fix stuff? And finally, be really clear when all the tests pass. This iterative process can be very unclear for the reader because a lot of what you're reading is broken code. And you're sat there thinking, well, hang on, what is working, what is not working? Make sure you signpost at the end of each section, oh, all of this is now working, actually this one I couldn't get working. Be really clear what is and isn't working before you move on. Okay, so be aware that to you it might make sense, but to a reader they might get very lost very quickly if you're not clearly ending with a nice review. Okay, let's move on to the more, I guess, coded aspects of this. So the kind of middle bullet points in this mark scheme, which is just about the quality effectively of your source code. So the code you've written, how good is it? Of course, we're looking for your solution to meet your requirements, but actually it's not always directly assessed, at least not here. But we're looking for how well written is the code. As we know, you can solve a problem with just dreadfully written code. It's just so messy and confusing and buggy. We're looking for high quality, well engineered code, you could say. Now, for each of these points, specifically they're looking for, first of all, it to be well structured and modular in nature. So you've got things like separate source files. You haven't got one 2,000 line Python file, for example. We're looking for subroutines, again, not just one huge program. You've got nicely broken down, specific, loosely coupled subroutines. And maybe if you've got object-oriented, which is not needed, maybe if you have, you can argue that you've got those classes not attached, they're encapsulated, etc., to again be well structured and modular. The next couple are about sort of annotation and naming, which are easy. And if you haven't got comments and if you've put silly names for your variables and so on, it's just unbelievable because it's so easy to get high marks for this. So add comments within your code, not just in your report, but actually within the code to explain complicated and important aspects. Don't add a comment to every single line because that's just awful to look at. Focus on maybe one comment for every subroutine with maybe another few if there's anything particularly complex within that subroutine. And the names of things like subroutines and variables and your arrays should be clear and understandable. Something like menu 1 or sub 5, not clear. It should self-document what exactly it is. And finally, I mentioned before, validation is really important, making sure that your program is robust and doesn't break immediately when a user types in something a bit weird. So your programming should be defensive. You should be expecting weird stuff to happen. So using exception handling, using validation routines, and you should really signpost this when you are talking about your report. Don't assume the person reading will spot this. Be super clear when you've used it and what effect it has. When you're testing, explicitly test for validation for robustness. Now, nothing on this mark scheme mentions testing actually at this point. I mean, review needs testing to have taken place, but this is because testing is its own separate criteria worth 10 marks and only 2 marking points for this, which shows they are important individually. The whole point is you are proving that you've done testing throughout. This whole iterative process relies on you doing testing as you are coding. So that you write some code, do some tests, some pass, some fail. The ones you fail, you go back and fix before testing again. Then when you're happy, you move on. We need that kind of natural iterative cycle in this report. So I think test tables are really the way to go, but not the only way to do this. Now hopefully you've got kind of a skeleton of these from design. You've planned out this already. Maybe with test data, I'm realizing my table here hasn't got test data, which would be a better thing to include possibly. But you've got tests, and these tests are very tied to the code. They're not kind of end user tests. They're focused on specific parts of your code. So don't be afraid to name drop particular subroutine names or particular algorithms within your code, because we are doing white box testing here. It's very under the hood, very specific to what exactly you are doing. Now, you should say which one's failed, which one's passed. You can see on the marking criteria, you've got to provide evidence of any failed tests and give justification for any actions you took to fix them. So this IO error I encountered in this made up scenario, I would then try and fix and then test it again and check it is working and say why I did what I did and why it worked. Now, provide evidence, so screenshots and videos. I think videos are great in many cases. I'll come back to that in a few minutes time, but it can't just be, yeah, pass, yeah, fail. You've got to show the person reading how you know this, and it will be a lot of screenshots, a lot of videos, and so on. Now, you're not going to have a million tests per module. You might have only say 10 tests per module or roughly, because the point is you're doing it bit by bit. You're building up in fairly small chunks. But we're not looking for, 2 tests per iteration, because that's too small. You're going to have just a million pages of content. Try and do it in nice chunks. And my example doesn't show this, but be really clear when you are testing for robustness. Like I've kind of suggested before, it can get lost in your source code because a validation while loop can be quite understated, but they're important, and so be really explicit when it is a test for robustness. Now, as I've kind of said, if you fail a test, show what you've done and justify how you fixed it. If you did, you might find certain tests you can't fix. Be honest about it. That's better than just glossing over it. Now, don't just when you fixed a test, when you fixed an issue, test only that again. Don't test everything again, because again that's going to be 1,000 pages of repetitive tables. Try and streamline it to just the stuff you need to be looking at. And when all of it passes, you're not done, because you've got another set of tests to do for another bit of code. So we've got several iterative cycles within this section. Okay, hopefully that makes sense. It is a confusing one, and this can quickly become a complete mess, which is not really what you want to hear, I'm sure. It can be a mess for you to do, it can be a mess for the person reading, so good planning can avoid a lot of these issues. And hopefully I can give you some specific mistakes which would lead to it becoming a mess, and hopefully you can avoid those. Now, don't document every single thing. You've got to be selective here. You could, in theory, add a comment to every single line of code. Waste of time, text or space. You could screenshot every single thing you've done. You might write a couple lines of code, screenshot it, do some tests, write about it. Oh, that would be exhausting for you and exhausting to read. Like I say, focus on a nice subroutine or a nice feature and do screenshots for the parts within that. I do think for testing, videos are great, especially when you've got motion. You can record a quick screen capture and show that more easily, but also for tiny tests like clicking a button or typing something in, etc., a video can show that much more easily. You're not wasting time cropping screenshots, making them fit, dealing with Word, formatting it weirdly. Videos are often really useful. We don't want 1,000 videos, but if you've got, say, 5 big videos throughout, great. And again, like I've kind of implied, don't document every single thing. Focus on the key areas of your solution. We're not interested in if statements or how a for loop works, unless it's particularly interesting. Another mistake is repeating tests without any need. If you've designed it properly, you know what's needed and you can remove any tests which are unnecessary. And once the test passed, forget them. You might effectively test it again in a sense later on in evaluation, but if it passes, delete that row in your next table and just focus on the ones which failed. Another mistake is focusing on the wrong kinds of errors. A syntax error is an error in your grammar of the language, right? If you've missed a colon, why are you telling us? Just fix it. That's not a big deal. But ones which are interesting are the runtime and logic errors, which can be tricky to fix. We want to focus on those, not a simple error you can fix very easily. Another mistake is people passing almost every test straight away. They look at this iteration and think, if I can avoid doing this, I will try to, and so all of their tests magically pass. You won't get marks. You need to show tests failing, and you need to show you correcting these failed tests. It's part of the mark scheme, and it's not showing weakness. Other people will pass all of their tests not through laziness, but because they don't want to show any sign they're not a good programmer. But again, it's part of the course. All of us have errors all the time when coding. OCR are just trying to make this clear and make this an important part of the NEA, right? We're just documenting it. If it wasn't documented, you'd still be having errors, you'd still be fixing errors. So, final thing I'll just emphasize again is, it can become messy if what you're writing about is not clear. You need to be definitive, what works, what doesn't work, before you move on or before you iterate. Just loads of code, loads of screenshots, loads of tables are hard to follow. If you can break it down and do summary bits, if you can do like mini conclusions before you move on, would be really helpful to the user. I would personally, right at the end of this section, have a nice big table summarizing what tests passed, what failed, what were the key issues, just so the person marking it has got a really clear idea what did work, what didn't work. If you feel your source code has been broken up to such a huge extent that it's really unclear, put in the appendix right at the end of your report all of the source code, paste it in so that it can be seen in one go if you think that actually it being broken up doesn't quite do it justice. Okay, moving on to the last section of this report, which is worth a good amount. It's worth 20 marks, and again, this should be, it's not massively straightforward, but it's a good way to gain marks without loads of difficulty if you've really understood what is required from this section. So, to be clear, the iterative testing is done as you're developing. All of this final section is done once all of the coding is finished. There should be no more coding after this point. Now, when marked has 2 points, it has 2 parts, which could be, this time, actually headings in your report. They could be under one subheading, they could be merged together. It's really your call, but they could be separated if you want to. First one is testing to inform evaluation, worth only 5 marks. That name I think is a little bit clunky. I'd personally call it post-development testing, and then just evaluation of your solution, worth 15 marks, although a fair few of these marks are really tied to this post-development testing. Now, for this final post-solution testing, test tables again are great. We want test tables which clearly explain what tests you're doing and the outcomes of these tests. So you're doing some more testing. This time, the tests are of the system as a whole. So not the individual parts, the individual bits of code. We're looking for what are the main features of it, do they work, do they not work, and so on. So we're linking these back to the goals set out in analysis. Hopefully your success criteria are relevant again here. And the 3 parts we're testing for are functionality, robustness, and usability. I would personally be tempted to have 3 separate test tables for each of these 3 areas. So functionality is about what does it do? Does it do this feature, yes or no? Usually quite plain, usually quite simple, maybe quite a long test table. Robustness, like I've said a few times, is about checking, does it respond well to weird inputs and errors? Will it crash? Is it stable? Etc. And usability is much more about when it is sat in front of your end user, do they understand what's going on? Can they use the features? Are the features useful to them? You know, some of the functions might work, but might actually not be very useful to your end user. So the first 2 you can do yourself. The last one, in an ideal world, you can get an end user to be involved and to help you with that. One thing I forgot actually, which I'll just mention really quickly because it might be relevant if you're aiming for extremely high marks in this project. This review section, a lot of it is you saying whether your code works or not. But again, if you can get a sign off from a stakeholder, that would make it even stronger. They might, approve a certain feature as you're developing it. That would be really nice. Now, all this stuff, going back to how you might show evidence. I'm a big fan of videos. I think screenshots are so clunky and take up so much space and are so tedious to do. If there is motion, in particular, videos are great, but also they combine lots of small tests in one go. If you're really organized and you've got a test table, you can have a test table in front of you and just record your video using free screen capture software and just go through it and upload it to YouTube and put the link in your report. Just be careful, if you have got loads of video links, don't tinker with them afterwards. If you say change it from unlisted to private, or you remove it and put a new one up, or delete your channel or whatever, your teacher might be able to see it, but when it's moderated a few months later, the moderator might try and open your link and it might not work. It's happened to me many times where I've tried to watch videos in reports and the link doesn't work, and so you can't give marks if there is no evidence. It's why providing some screenshots at least as a backup is always sensible if you want to be really safe. But for all your tests, provide some evidence. For usability, a lot of the evidence might be more qualitative, might be more written. You might actually ask for some written feedback from your stakeholder. So as I've said, involve them if you can and get their feedback. It might be for a survey, it might be for an interview if possible. And again, to emphasize, this testing is not about individual tiny bits of your code. It's about how the whole system works together, and don't try and repeat loads of tests from earlier. We're not focused on individual parts of the code. Now, this is only worth technically 5 marks, but the second main part is worth 15, and a lot of these bullet points, if you read, do connect to what I've just said. So for example, you've used the test evidence to cross-reference with the success criteria to evaluate and explain how your evidence shows that it's been met. Well, you could quite easily in your test table link it to your success criteria and have a column where you've explained whether it's been met or not and how you know that. So a lot of these bullet points actually can be done within your testing if you are going to separate the two sections. I'm not going to read through all of these bullet points because I would personally do it in a little bit of a different order. So I'll go through that instead. I think all of these are relatively simple to understand, I would suggest. So I would start by saying what this first bullet point is. What did you meet and how do you know this? What was not met? Be really honest about what maybe didn't quite work and what you were hoping to do but it didn't work and why it didn't work. Then we're looking at what is the quality of your code like. Maintainable code is well structured, well written, really clear, really readable. The idea being that somebody else or even yourself down the line could extend it, could make it better. And so you should be reflecting on your code style. What was effective, what wasn't? Was it well structured? Did you add lots of nice comments? That all answer that question. And reflect on how it helped you. Now, quite possibly you adding comments didn't help you, but say it did. Say it helped you understand what was going. When you left your project and came back to it, it was more clear, etc. Then, which might be linked to the first point, what improvements could be made? What things are you less happy with? What things didn't quite work? And if you've got any great ideas for extensions, how could you extend it? How could you do this down the line? And then importantly, you are getting reflections from stakeholders. What do they think of it? Were they happy with what they did? And what evidence do you have for this? Again, this could be quantitative, it could be qualitative, ideally a slight range of evidence at this point. And linked to maintainability and improvements, did they suggest any ideas? Did they have any thoughts on how it could be improved in the future? That's a good thing to talk about. And a nice way to wrap up this whole project is reflections on if you were to repeat a project or do a similar one in the future, what would you do differently if you could? And I think at this point, it's important to be really honest. Not every project is a roaring success. Not every solution is exactly as the person wanted, but you can still pick up lots of marks if you are honest and complete this evaluation in detail with lots of nice, considered arguments. And for stakeholder feedback, at this point, it's very tempting just to make this up completely and be massively positive. I've seen people say stuff like, "Oh, what an incredible project. I can't believe you did this. This worked perfectly. There are no bugs at all." And you're reading it thinking, there is no chance this CEO said that. And so, more honest the better. Try and get some real useful feedback if you can. Okay, right, those are our 4 sections done. Really well done if you managed to get through all of that. Hopefully it was useful. It's a big information overload, I'm totally aware, but it's important to have a good sense of the entire project, no matter what stage you are at. So these tips are just random things I was thinking about when I was obviously planning this video, which will hopefully be useful as well. So I think going back to the idea of picking an idea, don't feel pressured at this point. You might pressure yourself to come up with a brilliant idea. I think a lot of us, we can probably admit shyly, a lot of us pick computer science to come up with, the next big thing, right? Invent a Facebook or a Google or an Amazon. That's often a motivation when you're 15, 16. That may happen here. Hopefully it does, and you give lots of credit to me. But ultimately, it's just a project for an NEA. Keep the scope fairly simple, ideally with room to get advanced if you can. Focus on a few key features, and if it goes well, you can add more stuff to it. Try and keep it simple. If it's boring, that's a shame because you've got to spend lots of time on it. But ultimately, it's work for school. It may not fascinate you, depending on your idea. Now, very daunting, and this video might have contributed to it because of the amount of information and the amount of things I've said. It is daunting because a lot of it is on your own, quite honestly. Your teacher might give you time in lessons, but certainly at my school, we rarely spend time on it in class. I assume people are working on it at home. But it's really doable. And I think in particular this OCR NEA is good because not a lot of marks come from your actual solution. So if you find programming hard or it's new to you or you get really, really stuck, you can still get lots of marks with your other work and your write-up. Just to give a few specific things related to this, start as early as you can. As soon as your teacher says go, get on with it. Now for some of you that might be too late, which is not end of the world, but if you are watching this and you've got a year to do this, amazing. Plan properly, so spend time getting your analysis and your design good, not perfect, but good. So get your requirements list down and make sure you're happy with it so you're aware of what you're doing. If you've got just a rough idea and you start coding, it's very easy to waste time on unessential features or skip out something really important. But adapt. The list you come up with fairly early on might be very ambitious, it might be unambitious, it might not even work. You'll have to adapt and go back and tweak your plans, which is fine. Just be flexible. Don't get too stuck in your original thinking. And you are going to get stuck. Every single programming, even a tiny task you might do in class, you're going to have errors, you're going to get stuck. Many, many, many hours of my life have been spent, pacing around in an awful mood because my code didn't work and I couldn't fix it and I was annoyed and stressed and upset. It happens to all of us. It's partly why programming is really satisfying, because when you fix these bugs, you get happy. But take breaks, get out of your house, go for a walk, leave it a few days if you've got that luxury of time, because often a clear mind will help you fix and find motivation. Of course, it's a fine line between taking breaks and leaving it for 7 weeks because you want to put off going back to it. Try and force yourself to not leave things too long. Now, linked to this will be accountability, trying to hold yourself accountable. So if you've got a schedule, making sure you are following it or checking when you're on track, you're off track. You might sketch out your 8 big features and put it on a calendar and try and work towards these deadlines. Now, you might be good at that. Personally, I wouldn't have been good at that when I was sixth form age. So if you can get family or friends to hold you accountable by checking in on you and kind of pressuring you to do it, great. Because you need that peer pressure on occasion. But don't leave things late, of course. programming in particular you can't leave late. Some coursework you might be able to get through with an all-nighter and a few energy drinks, but programming, I personally can't leave last minute, because when you get stuck, that pressure compounds and it becomes even harder to fix these errors. So if you leave it late, and in particular the most important features, very high risk, very high stress. Now, again, some of you watching might not have a choice at this point, so you've got to do what you can, but if you have got a chance to plan properly, get on with the important stuff early. But don't jump in too early before you've got a good understanding. Make sure you know the techniques you're using before you start and understand them. For example, somebody might want to do an Android app. They might have never used Java before, never used Android before. They watch a half-an-hour video on YouTube on Java or Android, copy it into Visual Studio, and try and figure their way through the project by cobbling together tutorials and bits of code they found and all that sort of stuff. Really tough, because you don't really understand what's going on. Better to spend a week learning Android and then starting from scratch, applying what you know and building it up a lot more naturally. Quite possibly you start a project with no idea what you're doing. You've got to learn, and you've got to take the time to learn what to do. And it's not on the slide, but the amount of time it's going to take you is not fixed. It might take somebody 100 hours, it might take somebody a bit less, it might take somebody a lot longer. I've heard of people spending a half term on it and that's it. I've heard people work on it for month after month after month. There's not a single way to do it, unfortunately, but it will take a lot of time, and a lot of time usually over a fairly broad set of weeks or months. Now, before you get started, or if you are stuck when you are getting started, find some exemplars, so some previous projects, ideally both high and low. A lot of the time you're looking at the high exemplars, which can be even more daunting because some look amazing and you think you'll never get to that standard, even though you probably can. But the low scoring ones might give you some more confidence. Somebody who got a C, you might look at that and go, okay, well that's actually pretty doable. I can definitely improve on that. Now your teacher will have access to a few exemplars, so speak to them and ask them to show you some. I've showed you bits of a mark scheme. Make sure you have a read of the specification yourself in your own time and print it and refer to it. And before you submit your report, double check you've met as many of the points as you can. I mentioned peer pressure is good in certain areas, maybe not so much with your project ideas. Don't be too swayed by what your friends are doing. If 5 of your friends are doing first-person shooter games, that's not necessarily a good sign. You're meant to do different projects. Their ideas might not be as good as they sound. Their progress might not be as good as they're saying. Or on the flip side, they might be saying they're doing nothing, but actually they're doing loads of stuff. Focus on your own project. Don't think too much about what they're doing. And the main evidence you're giving is your report. The code is held inside in bits and pieces within your report, but a lot of it is just text, and how you structure it and how it looks will influence your mark to an extent, right? You should reference it, and you should definitely proofread before you submit. If you've got loads of typos and it's badly written, the content might be good, but it might bias the person marking it or moderating it, and they might think, oh, this person's not as good as actually you are. So check it's up standard, add page numbers, add a contents page, and make sure you reference it properly. And throughout, do your best to make life easier for the marker and moderator. Put in links, put in clear titles and subheadings, and links to certain pages if you're cross-referencing. For the iterative solution, please structure it in an easy to follow manner, like I've suggested. Otherwise it can become 200 pages of just screenshots and a bit of text, a bit of code. Try and structure it to make things easy for these poor people having to actually read and assess your work. And the last slide, the last set of things I'm going to say, you'll be glad to know, are these. So maybe you know this by now, but a lot of this is you learning it on your own, not necessarily things you've been taught in school. You're going to have to go away and learn this language or learn this technique or learn this algorithm. You may know it already, you quite possibly won't. And so that can mean you can't always get the help you might want. If you know more than your teacher on this very narrow area, you maybe can't get specific help. And so it's a lot of independent work. It's a lot on you, which is why you spending time on it outside of lesson is crucial. Now, we all know in programming, a lot of what we do is Googling errors, Googling for solutions when we get stuck. Be really careful borrowing, quote unquote, code. We know the kind of chief suspects. YouTube is great for learning stuff yourself, for good tutorials and so on. Not every tutorial is good, of course. Stack Overflow is a good forum for fixing errors in particular, and GitHub is a big website where people upload previous projects and you can see their source code and see what they've done. Now, all three are dangerous in their own way. I won't go into details of what I think makes it dangerous, but of course, code from somebody else can be confusing, it can be badly written, which will affect your marks in the code solution bit. And of course, the kind of bigger issue is you could well be plagiarizing. If you've taken a line of code from Stack Overflow, put a link in to credit it. GitHub, you shouldn't really be using code on GitHub because it's not your code. But you could get disqualified, you could get in lots of trouble if a marker recognizes a Unity tutorial or a famous GitHub project or a common tutorial on YouTube. You get in lots of trouble if that is spotted. And I've seen it before where people get brought down a lot of marks because they just followed a tutorial and it was recognized. The final point I will make is please do ask for help when you need it. Your teacher might not be able to help you with a specific error, especially if it's not in their field of expertise, but they can give you advice and motivate you, and your friends I'm sure will be supportive and your family will be supportive just from an emotional point of view. Programming is grueling and can be very up and down. You need to acknowledge that, it's very from one emotion to the next at times. It's a marathon, not a sprint in this project. And again, it's only worth 20%. So ultimately, if you have a nightmare and things don't really go so well, you can try and use your report to bring up your marks, but also it's only worth 20%, not the end of the world. But look, really exciting. It's a fantastic opportunity. Hopefully you make something really cool and you're really excited by doing this project. I hope it goes really well and best of luck with it all.